Okay, so the next thing you're going to do is assign students to do steps 6 through 8, and then you're going to walk around and help them. So on step 6, it's asking them how the pattern of growth actually affects the rate. So we saw in the previous question that the slope is increasing every generation. So the slope keeps getting bigger and bigger. But what is that actually doing to the rate at which the population is growing? So on this one, they're going to calculate the rate, but make sure they use expected numbers. And it says it in the question, but students always miss it. Because if they use their actual data from their fly populations, their numbers are going to be all over the place because of probability. And so have them use their expected numbers. And so, all right, so and let them struggle with this. We see all kinds of creative answers here, and you want to sort of get them thinking in the right way, but not do it for them. Okay, so we can say, all right, from generation, I put my number of generations up there. From generation 1 to generation 2, I went from 2 to 12. All right, so it's pretty easy to see. I got 10 babies. But where students mess up is, what do I divide that 10 babies by? So I got 10 babies in one generation. Is it 10 babies out of the 12? Well, that doesn't make sense. We didn't get 10 babies out of the 12, right? So that's not right. We say, no, you don't want to divide it out of the 12, 10 out of 12. But sometimes they want to divide it by the 12. Sometimes they want to divide it by somewhere in between. So somewhere in the middle of the population, we were at 8. And that's fine. They can do it that way, like somewhere in between the generations. That's going to give you a more continuous rate of growth. But tell them, for this lab and the purposes of these fruit flies, we know 1 week, 1 week, 1 week. So we're going to use a discrete growth rate. Okay, so there might be some mathematician people in there like, oh, it needs to be continuous, so we need to use exponents. No, say don't overcomplicate it. Okay, all we want to do is look at, we got those 10 babies out of how many flies? We got those 10 babies out of the original 2 parent flies. Okay, so our growth rate is 5.0. And then going from generation 2 to generation 3, okay, 72, wow. So we went from 12 to 72, so 72 minus the 12, okay, and how many did we start with? Well, we started with 12. We got 60 babies out of the 12 original, okay, and so that gives us 60 over 12, which also gives us 5.0. Then you can do the same thing. We went from 72 to 432. So out of the original 72 flies, we ended up with 432. Okay, and that also gives us 5.0. So they should get 5.0 for every generation that they do. And so then number 7, it says, based on your calculations, how does the growth rate vary across time? Well, it doesn't change. And you need to have the students think about this logically. Say, all right, so we know that the slopes change. That means that the more flies we have, the more babies we're going to get. But let's look at one individual fly. That one individual fly, does it have more babies when there's more flies around? Or does it always have the same amount of babies? Does it always just have the 10 offspring per couple? Or is as we get more flies, more babies are being born for each fly? Well, of course not, right? So they think about it logically. The rate at which we're growing should stay the same because each fly can only produce so much. And then they're supposed to write for number 8 a generic expression, like how did I do this? Well, in order to get that rate of 5.0, I took the number of babies, right, and I divided it by the initial population. And they can come up with any number of mathematical expressions they want, and I would encourage them to put it on their little whiteboards and then have a share session out so that everybody can see what they used. I like the number of babies over the initial population, but or that some people like to write n2 minus n1 over n1. That works too. And so you're going to have them write that down. Okay. And then going back to this idea that a fly can only produce so many babies. So it doesn't matter if the population keeps getting bigger, a single fly can only produce so many babies. And that's so many babies that they can produce. This R, it's determined by every individual fly and how much they can reproduce, is called the biotic potential. Whoops. Or intrinsic growth rate. Okay, so R, and we often write it as R max. It's the maximum amount that this particular organism can reproduce. It's their biotic potential, and I probably heard that term before when you guys did natural selection, that in order for natural selection to take place, that the flies have to be growing at their biotic, or the population has to be growing at its biotic potential. What that means is they got to be growing at their maximum. So if you look at humans, for instance, what's our biotic potential? Well, technically, we could reproduce about every 1.5 to 2 years, right? Because we've got about almost 1 year incubation time, and then a 1 year breastfeeding time. And so about every 2 years, 18 months or so, a human can reproduce. So if you were reproducing every 18 months, that would be your biotic potential. Now, we don't reach our biotic potential for various reasons, but the fruit flies, they're doing their darndest to reach their biotic potential by producing 10 babies every week. Okay, so that's the R max, and you figure it out by this formula. Okay. Okay, and I'm going to stop it again. We'll do the next segment in a minute.